everyone. Alright, let's go ahead and let's get started for it. Alright, so for your homework, you had on page number 130, number 7, and 1 through 5 on page 134. Alright, so number 7 first off. What process do hydrogen bombs use to produce an enormous amount of heat? That's nuclear fusion, not fission. We'll talk about the differences later on today. Alright, on 1 through 5 on page 134 to 135. So, what are the valence electrons? This is electrons in the valence, or the outermost shell of an atom, and we'll talk more about that later on. State the octet rule. Alright, most atoms tend to react to obtain 8 electrons in their valence shell. So, octet or octagon, that oct typically means 8. So, an octagon has 8 sides. So, the octet rule is saying they want to have 8 valence electrons. So, I'll help you to memorize it. Number 3, what does the periodic law state? When elements are arranged by their increasing atomic numbers, they show regular and repeating or periodic properties. So the idea is you have this pattern over and over and over again. Number 4, what is the periodic table of elements? A table of elements arranged by atomic number and number of valence electrons. We're going to talk about how you can use the periodic table later, and it's a very handy tool that a lot of scientists use and like. Number 5, what term refers to a column? Sorry about that, I started early. What group refers to a column in the periodic table of elements? So remember, a column is the up or down portion for it. So that is a group. So a group is an up or down column portion. So make a note for those. Alright, so for your classwork to get you started and get you thinking about physical science, is I want you to copy down the bold terms and definitions. Remember, we haven't been doing this a lot because your periodic table quiz was yesterday. I think a good job overall for that. So, because of that though, we haven't copied down a lot of terms and definitions, so this is kind of help you to get started and thinking back over it. So go back to page 160, copy down the bold terms and definitions from page 60 to about to page 123. So only copy down the bold terms and definitions just twice today, as many as you can. Most of them you should already know that, okay, I know what an ion is, what a cation is, what a proton is. This is to help you just kind of get mentally started and get going, because remember, we haven't had a quiz over this material yet. So you need to start thinking about it and getting ready for it. I know your big focus is on the periodic table, and that is fine. But make sure you're also shifting gears mentally and you're getting ready to be studying your terms and definitions as well, and not just trying to cram them. So go ahead and pause your video. Only about 5 to 10 minutes though. Don't spend too long. Alright, if you're watching this, I'm assuming that means you already finished your classwork. So let's go over some of those bold terms and their definitions. Alright, so first off, what is a subatomic particle? This is a particle smaller than an atom. So these are small particles of matter that make up an atom. Your book talks about 3 of them in particular, so 2 of them are in the nucleus of the atom. So what do we call a substance that's in the nucleus of the atom? We have a special term for it. Nucleon. So remember, what are the 2 particles in the nucleus of an atom? Protons and neutrons. Which one's neutral? Neutron. So the proton is positive. So the proton has a positive charge while neutrons have a neutral charge. Alright, what determines the identity of the elements? The protons. And then what term refers to the number of protons? Atomic number, because it determines the identity of the atom or of the element. Alright, can you have a different number of neutrons? Yes, so if I have an atom like carbon, so we use carbon a lot for this. So if I have carbon, remember carbon has how many protons? You don't have to memorize this, but you probably will. 6. Carbon can have can have a mass number of 12, or it can have a mass number of 14. So you'll sometimes see it written like this, or you'll see it written like this as well. Alright, so what do we call these to where they're both carbon, they both have an atomic number of 6, but they have a different number of neutrons? What do we call these? Isotopes. Perfect. Now, what do we call that top number on the top left whenever you write an element like this? What is this number that tells you the number of protons and neutrons together? The mass number, correct. So this one also has 6 neutrons, this one has 8 neutrons. Alright, what do we think makes up protons and neutrons? Quarks. Good job. Alright, what is the negative charge that's found surrounding the nucleus? Electrons. Perfect. What do we call that layer that's around the nucleus that can hold so many electrons? Electron shells, or the energy levels for it. Alright, can you have an element like carbon lose or gain electrons? Yes, you can. What do we call it whenever it's lost or gained electrons? What's the general term? An ion. Perfect. Alright, what do we call it if it's gained electron? Like we'll say carbon has gained an electron, will be positive or negative? Negative. So, what do we call it specifically? Anion. What if it's lost an electron? So it has a positive charge. Cation. Good job for that. What are the units we use to measure the weight or the mass of an atom? Because atoms are so tiny, you can't use grams. Atomic mass units, or AMUs, or just use, those are all fine for it. Alright, what do we call the average weight? Like if you look at the periodic table on page 131, you'll notice carbon has a weight of 12.1 AMUs, or just U's for it. So, how do we find, like, what do we call this? The average atomic weight. So, make a note, I think I might have said that by accident when I was explaining it. So, average atomic weight, how do we find that? It's all the averages of all of the different isotopes of carbon plus how much we find of the isotopes of carbon as well. So you may know this is the average atomic mass, and typically that's the number we use to say, okay, most carbons weigh this amount, or this is the average based on the isotopes and the number, the amount of the isotopes. So this is what we're going to consider the average. That's what your periodic table has that number listed. Alright, thinking about the different scientists. Alright, so who came up with the quantum theory saying that the electrons have to absorb or gain these packets of energy to jump from one level to another? Max Planck, good job. Who came up with the Bohr model saying okay, if you have to absorb or gain these energy packets, and that means that they're locked in their orbits, that they can't jump from one to the other unless they have an energy packet. So that's Niels Bohr with the Bohr model. Who came up with the wave mechanical model, saying that the electrons move in this wave pattern? I cannot do this motion. So that is Erwin Schrödinger. So make a note for him. Who came up with the uncertainty principle, saying you can either note the position or note the velocity. You can't know both at the same time. So Werner Heisenberg. So Werner's how it looks like. So Werner Heisenberg, he came up with the Heisenberg uncertainty principle. Sometimes you see it written like in chemistry next year. They just call it the uncertainty principle. So if you write uncertainty principle, I know what you mean, but your book describes it as the Heisenberg uncertainty principle. So it helps you to remember, okay, the scientist's name with it. That's fine as well. Alright, who came up with the electron cloud model, saying that, okay, you have these orbitals, these regions of space, because they're moving in this wave pattern, and because you can't know their position and velocity at the same time, then here's a region where they're probably at. So who came up with that idea with an orbital? Max Born. Make a note that the orbitals are with the electron cloud model. So electron cloud model has those regions of orbitals. The Bohr model has orbits where they're locked into like a ring or a circle. Alright, so what do we call the four numbers that represent the position of the electrons around the atom? The quantum numbers. Good job. So the overall motion of each electron can be mathematically represented by four quantum numbers, stating the energy level, or the shell, the shape of the orbital, the orientation in space, and then also the spin of the electron. What principle says that no two electrons in an atom can have the same set four quantum numbers? They can't exist in the exact same spot at the same time. It won't work. So the Pauli exclusion principle. Alright, so we talked about it. So we talked about whenever the nucleus breaks apart or undergoes a change, we call that nuclear radiation. What do we call an element that is unstable? There's a better term. Radioactive. Good job. What do you call that process whenever you have the atomic nucleus breaks up or changes, emitting radiation? This is a two-word answer. Radioactive decay. What do you call the length of time it takes for one half of the substance to decay into a new substance? What do you call that length of time? The half-life. Good job. So that's the idea of what it takes. Okay, like let's say I started off with a substance that has 16 grams of this radioactive substance, and so let's say it has a half-life of 10 years. It doesn't, we're just making this up. So 10 years, so every 10 years, half of it will decompose into the new substance. So if 10 years pass and half of it decomposes, how much of the original substance will I have? 8 grams. Well, if I wait another 10 years, check it again. 4 grams. What if I wait another 10 years, check it again. 2 grams. And so it's the idea that every 10 years, if that's the half-life, half of it will have changed. So that's the idea for a half-life. Alright. Talked about three different types of radioactive decay. What type of decay is it whenever you have an unstable atom ejects 2 protons and 2 neutrons? What type of decay is that? Alpha decay. We draw that one with a little fish-looking symbol. So, not perfect, but it's the idea of an alpha decay. Alright, so the alpha particle is basically what though? If it has 2 protons, what element is that? Helium. Good job. So it's helium. It has 2 protons. Now it also kicks off 2 neutrons. So what's the mass number? 4. Perfect. So this would be the idea of an alpha particle for it. So your book points out it's basically a helium-4 nucleus. It doesn't have the electrons. So technically it has a 2+ charge because there's no electrons with it. It just has the 2 protons. But your book's just pointing out that it's just the nucleus of the helium atom. So remember, that's alpha decay. Alright. Beta decay. What happens with beta decay? That's whenever a neutron changes into a proton and it kicks off an electron. What's the symbol for it? Right, it's the bee-looking thing with the tail. So beta decay, that's whenever you have the neutron changes into the proton and it kicks off an electron for it to balance out the charge. Because let's say we're just going to keep using 4 carbon because carbon's my example today. So if I have carbon undergo alpha decay, we'll say it's this carbon. What does carbon become if it undergoes alpha decay? Remember, it's losing 2 protons and 2 neutrons. I actually don't remember what's 2 under carbon. I have to look. Beryllium. So, Be. I had to go look at my periodic table because I could not remember. So, Be4, because remember, it lost 2 protons, and then it lost 2 neutrons as well. So, this would be, that's not correct. This would be beryllium 8 specifically, because it has 4 protons, but it has 4 neutrons with it. So that'd be the idea of alpha decay. Let's say we have our carbon undergo beta decay. If it undergoes beta decay, will it still be carbon? No, because remember the proton changes into the neutron changes into the proton. So 7, what element has the atomic number of 7? Nitrogen. Now does the mass number change if you have a neutron changing into a proton? No, it does not. So this still has a mass number of 12, and then it kicks off an electron to balance out the charge for it. So that's beta decay. Gamma decay, what's the symbol for gamma decay? It has a Y-looking symbol. So it looks like a Y, so it's a little bit skinnier looking one, but that's gamma. So gamma decay, this is whenever you have an excited nucleus, it gives off gamma radiation, these wavelengths of extremely high energy and frequency. Now, which one is the most dangerous if you just stand there and let it hit you? You shouldn't do that. But if you were, which one's the most dangerous? Gamma radiation, because that one can go right through your body. Alpha radiation is stopped by your skin, so it might hurt your skin, but your skin's okay. It'll be fine with it. Beta decay can get into your tissues before it gets stopped. Gamma just goes straight through you at that point. It can just go through your cells, and it can hurt whatever cells that it's gone through. Now, we're talking about how there's 2 good uses of nuclear radiation. There's other ones with nuclear power. But there's 2 major aspects of nuclear radiation. You can use nuclear medicine, so make a note of that. What disease do we use to treat nuclear medicine in particular with? Or chemotherapy is a more common name for it. Cancer, and then food irradiation. This one kills parasites because they shoot it basically with gamma radiation. Since the gamma just goes through the food, your food should already be dead. So having radiation go through it doesn't necessarily hurt it. But if there's parasites or bacteria, it'll kill the bacteria that's in the food. That's the reason why people use that. So bacteria and parasites are exposed to it. Some people still make them nervous about it, but in theory, it's fine. Alright, and we also use it to sterilize first aid kits, adhesive bandages, and other medical equipment. Alright, so now you're going to get into fusion versus fission. So if you don't have your textbook out, go ahead and get it out. Sorry, my nose is itchy. So go ahead and get your textbook out, and let's go over nuclear fusion versus fission. Alright, fusion is the one you read about last night. The first one you're going to talk about is fission. Fission sounds like division. It kind of rhymes. No, it's not spelled perfectly, so don't go off spelling for it. The nuclear fission is whenever you have one atom and it's splitting apart into 2 atoms. Your book points out that the main one we use is uranium-235. Alright, so uranium has, remember if it says 235, what is that? What's it telling you? That's not the atomic number? Right, it's the mass number. So 235 is the mass number. How many protons does uranium have? I had to look because I wasn't entirely sure. 92. Now, your book points out that whenever a neutron strikes the atom of uranium-235, the atom captures the neutron and it turns into uranium-236. So uranium turns, this first one turns into uranium-236. Now keep in mind, is it still uranium? Yes, because it still has its correct number of protons. It's just taking on an extra neutron now, though. But the uranium-236, that extra neutron is just enough to cause it to become unstable. It doesn't like having that many neutrons in the center of the atom. So rather than just kicking off the neutron, it breaks apart into two smaller elements. So the uranium-236 nucleus vibrates rapidly and can't hold itself together. So it splits apart or divides into two smaller elements. So it splits into several pieces into smaller atoms or free neutrons, and the process is called nuclear fission. So fission means division, so it rhymes with it. That might help you to remember it. It releases an enormous amount of heat energy and gamma radiation as well, or gamma rays with it. Alright, so your book points out that this can also have it, that the neutrons also generated by this radiation are also frequently considered a type of nuclear radiation. Next year in chemistry, we're going to talk about neutron radiation as well. So right now, don't worry about it. There's no alpha, beta, and gamma. But your book's pointing out that, hey, you can have a type of neutron radiation as well that is also dangerous, but don't worry about it because your book's just pointing it out for you. Alright, chain reactions. As you have this 235 uranium change into 236, and as it splits, it'll kick off some of those extra neutrons. Now those neutrons, if there's other elements of uranium-235 around it, other isotopes of uranium, that those neutrons can now hit into them and cause a chain reaction that way and cause them to split. So we call this a domino effect or a chain reaction. So make a note of that. This domino effect is a chain reaction with the idea of you have one uranium-236 split, and so now it's causing its neutrons to scatter and hit other uranium-235, cause them to turn into 236. Now they're unstable and they'll split, and it causes more and more and more. A chain reaction, though, cannot occur unless there's a certain amount of fissile material present in order to kickstart this reaction. We call this the critical mass. This is saying how much of an element has to be there, how much do you physically have to have a chain reaction actually get started. If you have too little, it's not going to get going. You have to have a bunch of it there. Your book points out for uranium-235, you have to have about 35 pounds of it altogether for it to even have this chain reaction get started and to have it just keep going and going and going. If you have less than that, it's not going to work properly. So, just make a note though, that this is the amount of material that you have to have, fissionable material, for it to even get going for it. The book points out it does vary a little bit. For plutonium-239, the critical mass is 22 pounds. So again, it varies a little bit from element to element. An uncontrolled chain reaction of 235 can split into trillions and trillions of atoms in a very, 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 very short amount of time. And it can also create a lot of heat and a lot of energy. We call a device that initiates an uncontrolled chain reaction an atomic bomb because it releases so much energy and so much heat all at once. So make a note for that if you have an uncontrolled chain reaction, the device that starts it is an atomic bomb. Now, we've dropped two atomic bombs in history. So, the United States in particular, these are the only atomic bombs that have been dropped. There have been atomic bomb testing, but we haven't used an atomic bomb on another nation. Alright, so what was the country that the United States dropped the two atomic bombs on? Japan, and do you know specifically what the cities were? Yeah, Hiroshima and Nagasaki. So this is a picture of one of the bombs. So I'm going to show you, here's what the bomb looks like. And then here's a picture of the explosion after it happened. It's hard to find accurate photos of this. There's a lot of artistic renditions of it because it was a very sad event for the Japanese people and also a sad event for Americans as well, with the idea of we're at war and we have to win the war. But again, this is one of the two times we dropped the atomic bomb on another country. And again, so finding photographs of this is very, very, very hard to do. Find a good photograph. Because a lot of the pilots, once they dropped the bomb, were going back to the United States. They weren't sticking around in the area to find out, does the bomb work? You hope it does and you leave. And so a lot of the fighter pilots were heading back to the United States once they dropped their bomb because they weren't sure exactly what was supposed to happen, but they knew they weren't supposed to stick around and find out. So they were on their way back. So, just make a note though that the device that initiates an uncontrolled chain reaction is an atomic bomb. Now, not every type of chain reaction can become an atomic bomb. So, your book has the picture showing nuclear fission at the bottom, page 126. I have an animation to help show that as well. So, this is what the idea your book is trying to show you. If you have nuclear fission, you have uranium excite or hit this uranium-235, and then it becomes excited and it splits off. Whenever it splits, its neutrons can hit other uranium-235s, cause them to change, and cause them to split as well. So that's what that whole diagram is trying to show you. So again, you have the neutron become unstable, it splits apart, its neutrons now strike other isotopes and they split. So that's the idea of nuclear fission plus chain reaction. So that diagram is very good at showing both ideas at once for it. So, in a lot of cases, you have to have a highly purified version of uranium-235. You have to have a bunch of uranium-235, and it has to be processed. It has to be pretty much pure of this particular type of isotope and you have to have so much of it to have a critical mass to even make a bomb for it. So that's part of the reason as to how come not every type of uranium is automatically a bomb for it. So, your book points out only highly purified samples of uranium-235 can react fast enough to produce a nuclear explosion. But the most common isotope of uranium is uranium-238. Not so much more common version of it, and that's not fissionable. It won't split apart. It's stable. So, the much more common isotope is 238. So this one, we find a lot more, and this is the isotope that we find out in nature, and it doesn't split apart nearly as much for it. Your book points out a chain reaction can occur if you mix uranium-238 and uranium-235, but it won't cause an explosion. We can use this and control it in a way so that we can use this to make energy. The rate of the reaction can be adjusted by absorbing some of the extra neutrons with non-physical material like cadmium or boron. And so because of that, this is the type of uranium we're using in nuclear reactors. Because there's a lot of hype and a lot of misconception about nuclear reactors. Whenever people see nuclear reactors, they automatically think bombs, dangerous, radiation, we're all going to die. And that's not happening with the nuclear power plant. So make a note, a type of controlled chain reaction that it is harnessed by a nuclear reactor to produce useful energy. So a controlled chain reaction that's used to make energy is a nuclear reactor. Now, most reactors, they use heat that is given off by the nuclear fission to produce steam. So a lot of cases, whenever people see these tall columns and this white coming out of it, they think, oh, radioactive stuff, that's dangerous. This is steam. What is steam made of? Regular steam. Water. This is just basically clouds coming out of the pipe. It's just water vapor. There's nothing dangerous in this particular section. The uranium, the dangerous portion, is typically in these little bitty domes over here. Even these brick-like buildings, those aren't even the dangerous parts of it. The dome portions, if you're looking at the picture, is more of down here in this section. So that's where typically the uranium is stored at. So what you see coming out of it is just water vapor. It's just steam at that point. It's not dangerous at all. So it offers a safe, clean, and abundant source of energy. Now, you do get nuclear waste, and unfortunately, nuclear waste is very dangerous and very radioactive. But your book points out that our regular power plants that use coal, they produce a lot of toxins into the air and a lot of pollution. So there is an argument to be made saying, okay, which is better? Having a whole bunch of pollution put into the air, or putting a little bit of nuclear radiation and sticking that in a hole or somewhere else safe to keep it contained and keep it safe. This is just water vapor that's coming out of the plant, and the only other byproduct really is nuclear radiation or radioactive waste. So in some cases you can even have a breeder reactor. They can actually recycle the nuclear fuel that they need. So your book points out spent nuclear fuel can often be recycled in special breeder reactors which produce more nuclear fuel than they use. They accomplish this by changing uranium-238 into plutonium-239 or changing thorium-232 into uranium-233. You don't have to know what elements they're using. But just pointing out that, hey, you can basically recycle it in a breeder reactant. So your book's pointing out again as well towards the bottom of the page with the idea of pollution comparison between a typical coal-fired power plant and then a nuclear power plant. So look at all of the tons of waste. So produced by year by a 1,000 megawatt coal-fired plant. So you look to see the carbon dioxide, excuse me. So it has 3,700,000 tons per year. And look at all the other waste. So solid waste, sulfur oxides, nitrogen oxides, airborne particles. These are tons, not pounds. So this is a lot of byproduct pollution put into the air by these coal plants. While the nuclear power plants, not really any dangerous for it, but they do have radioactive heavy metals. That's the idea. You can take it and store it somewhere. That's what it means by like heavy metals for it. Now, your book points out in some cases they can be recycled, but not all of it. So it's one of those, it's a risk assessment or choosing which one is more dangerous. If you're going to have energy, you're going to have to use something to produce the energy. So you can either use coal power, that's the major source of power for the United States. Now there's other sources of power like turbines, like with wind energy. But coal power is a major source of power. Or you could choose to use something like nuclear energy. So it's choosing which one is more dangerous. Unfortunately, a lot of people feel like because of the atomic bombs that the nuclear energy is more dangerous. But there is a very good argument saying that, hey, on the coal-powered ones, since they produce so much pollution and that causes other health effects, it might be better to switch over gradually to nuclear power plants. And because relatively they are very, very safe. We don't have a lot of problems with nuclear power plants. Your book does talk about, I believe, 2 major accidents that has occurred. Your book skips over a third one, but this one doesn't affect us in the United States. But your book is pointing out that, okay, that there's 2 major accidents, one in the United States and one over in Ukraine that affect nuclear power plants. So to make a note though for it, that one of the major disadvantages of nuclear power plants is how they do have nuclear waste, but it's a lot smaller amount than the airborne pollution, and we can store that in a place, maybe underground. And then we can also maybe reuse it in a breeder reactor or recycle it. Let's see, let me make sure did I skip anything. Oh, France, you talked about France as well. France uses a lot of nuclear power that they use predominantly nuclear energy to get their electricity. While in the United States, because so many people are scared of nuclear power, they don't want to use nuclear power energy. But again, other countries use it and they seem to be going just fine. Alright, so your book starts talking about how it works. So flip over to Chernobyl on the next page. Your book references Chernobyl on this page, on page 127. Just make a note now, unless Chernobyl, it was in Ukraine. This explosion of the plant caused at least 31 immediate deaths and exposed many people to large amounts of radiation. But then also explains it more on the next page. So let's go ahead and turn over there. Alright, several key factors led to the disaster at Chernobyl. Chernobyl reactor was inherently unsafe design that could not have been licensed to operate in the Western nations. Now keep in mind, this is whenever the Soviet Union had taken over Ukraine. Now, did the Soviet Union have a history of caring about the people that had taken over? No, it didn't. So they had built an unsafe design over in Ukraine and they were using it in Ukraine. The accident occurred while a group of Soviet engineers had placed the reactor in an extremely dangerous state to conduct an experiment. They shut off the reactor's safety and emergency backup systems for the experiment and overrode the computer that attempted to shut down the reactor. These and other mistakes overheated the reactor, causing a steam explosion that ruptured the roof of the reactor building. In the intense heat, the graphite in the reactor caught fire, and the radiation was released in a cloud of smoke that contaminated it in the surrounding countryside. So the scientists, they were conducting an experiment, and so they had to override the computer several times, telling it to keep going. Whenever the computer realized this is dangerous, you shouldn't be doing that, and they kept telling it, keep going, we need to see what happens. And so they caused this nuclear reactor to basically explode. Now technically it was the intense heat, and so it released the intense heat and radiation. So it's not like the whole thing exploded like a bomb. That's not what happened. But it's the idea of the heat caused it to spread out into the steam, and it caused the radiation to go out with it as well. So the graphite in the reactor caught fire, and the radiation was released in a cloud of smoke. And so that's the reason why it contaminated so much of the area around it. Alright, only 31 immediate deaths can be definitely attributed to the Chernobyl accident. Scientists believe that long-term effects of radiation exposure, such as increased cancer risk, may cause many more deaths. Estimates of the number of deaths from long-term exposure may vary widely, ranging from a few thousand to several million. Such estimates are complicated by the fact that doctors can't determine whether an individual case of cancer is due to increased radiation or due to other cancers. Because remember, your body can absorb small amounts of radiation and be okay. Kind of how like absorbing the sunlight. So the scientists aren't sure, well, which deaths or cancers are caused by the Chernobyl accident and which one is just part of living life. So they can't tell exactly who's actually sick because of Chernobyl or who's just sick just because it's how their body is. Alright, an accident like Chernobyl disaster is unlikely in the United States where safety is given a high priority and reactor designs follow stringent safety standards. Typical American reactors have a thick, tremendously strong pressure vessel made of stainless steel around the core itself. The core and pressure vessel are housed in a massive containment building made of reinforced concrete several feet thick and sealed with a steel inner liner. The containment vessels were designed to withstand an earthquake, tsunami, fire, reactor steam explosion, or even a direct hit by a jumbo jet. They designed them so well, saying, okay, if a jumbo jet crashes into the nuclear reactor, it will still not explode. They think of it that well and that far in advance for the designs in America. Alright, so going on from that. By contrast, Chernobyl's reactor pressure vessel was not intended to contain a major reactor failure, and the flat concrete roof was easily penetrated by blast. Because of the differences between United States and Soviet reactors, the 1979 incident at 3 Mile Island near Harrisburg, Pennsylvania, had a much different ending. In that accident, minor mechanical failures, compounded by a series of human errors, humans were also involved in being stupid, including partial shutdown of emergency systems, caused the reactor to severely overheat. Although a meltdown, this is a melting of the reactor's core, followed the pressure vessel and the containment shell performed properly. No one was injured or received any significant radiation. The residents near the plant received approximately 0.012 millisieverts, that's what the SV stands for, by the way, of radiation from some radioactive steam. The American nuclear power industry responded by modifying other reactors to prevent these accidents. So again, even at 3 Mile, even at the 3 Mile Island, even though that was humans again messing around whenever they weren't supposed to, the reactor did what it was supposed to. It had a partial meltdown. It had a partial meltdown of the core, but it didn't explode out. It stayed safely in the area where it was supposed to. Your book does not have this picture, but this is to kind of help show you what a typical nuclear reactor looks like. Okay, here's the steam portion of it, here's the actual electrical side, and then here's where you have the containment vessel, where the actual dangerous nuclear reactor is on the inside of it. So the nuclear reactor in this picture is the green part, but what they use from it is not even they're not using the radioactive material in order to turn turbines. What they use is they heat up water. And so all the heat from the water causes the water to turn into steam, and then the steam turns the steam turbines to actually produce the electricity. So it's not even like the nuclear power is actually generating electricity. They're just using all the heat from the nuclear reactor as you have the uranium splitting. Since it's producing so much heat, that heats up the water into steam, and now the steam is being harnessed to produce electricity. They have a different system of coolant water as well to help absorb the extra heat, and that's how come you have the steam coming out of the pipe like that water vapor. Because they have basically 3 different loops on the inside. You have the heat on the inside of the nuclear reactor, you have the water going through it that helps turn the turbines, and then you have the extra water to help cool it down, to help absorb that extra heat. You don't have to note your diagram, I'm just pointing it out for you. But that's the idea of a nuclear reactor. In the United States, they're designed to be very, very, very safe, so that way, they won't explode typically, and even if you do have a meltdown or have something really bad happen, it'll stay in the containment unit. So in the United States, our designs are much safer than the ones used over in Ukraine with the Soviet Union. Soviet Union, they used a very unsafe design. Alright, so make a note though, so nuclear reactors, yes or no, are they a good idea? This is something that you just have to decide and be educated on yourself. To decide, okay, which one's better? Coal-powered plants that produce a lot of pollution right now, or nuclear power plants to where, okay, they do have radioactive material, but that's a lot smaller amount, and we can store that under the ground, or we can also use it later on in breeder reactors as well. Alright, so let's look over with nuclear fission. Alright, so, sorry, I said nuclear fission. This is nuclear fusion. So nuclear fusion is what we think happens with the sun, since the sun generates so much energy. Instead of having it with fission, where you have the atom splitting, they think it's whenever you take a lot of pressure and a lot of heat, and you can make two smaller atoms combined into a larger atom. So this is nuclear fission. So the process of combining two nuclei to form a heavier nucleus and thereby releasing energy is nuclear fusion. What they typically think is that it's probably an isotope of hydrogens combining together. So what they think it is typically is that it's probably an isotope of hydrogen. So remember, if it's hydrogen, how many electrons, how many protons does it have? One. So they'll take one hydrogen atom, combine it with another hydrogen atom, and they'll get a new element, because remember, it has two protons. Now what element has two protons? Helium. So that's what they're showing you with this one, describing, okay, they think it's hydrogen 1 and hydrogen 2, or that is the intense heat of the pressure of the core of the sun, atoms of hydrogen 1, so hydrogen that has a mass number of 1. So for this first one, if you have a hydrogen of an atomic number of 1 and a mass number of 1, how many neutrons do you have? If you have an atomic number of 1 and a mass number of 1. Right, you have 0 neutrons then, because the mass number is describing the number of protons and neutrons together. So if I have one proton, no neutrons, I'm still gonna have a mass number of 1. So this would be hydrogen. A second isotope of hydrogen, again, still has 1 atomic number, so 1 proton, but it has a mass number of 2. So this one has 1 neutron. You have another version of hydrogen where it has 1 proton and then 2 neutrons. Your book describes the different isotopes and gives you their names. You don't have to know them this year. You need to know it next year, possibly in chemistry. But you don't need to know it right now. So it's hydrogen 1, hydrogen 2, or deuterium is the technical name for it. And then tritium is hydrogen 3. So your book's just describing them too. So they think that they are stripped of their electrons and fused to form helium. Heating the sun's core to possibly 15 million degrees Celsius. So very, 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 very hot. And the sun has been doing this since the 4th day of creation. So scientists say, that's a lot of energy. And it would be nice if we could harness the energy of the sun and get good, clean energy this way from it. They can also use it to make a bomb, though. So again, with a lot of energy, if you don't control it, it can be very dangerous. So the hydrogen bomb, this uses nuclear fusion, not nuclear fission. So nuclear fusion to release a tremendous amount of energy. We have not dropped this type of bomb on anyone. So the atomic bombs of Hiroshima and Nagasaki, those were fission bombs. We have not dropped a fusion bomb. We've tested them, but we have not dropped it on anyone. So your book points out the most powerful hydrogen bomb ever tested was a device that exploded with 50 million tons of TNT, about 2,500 times as powerful as the atomic bombs. So the heat and pressure required to initiate the fusion reaction, though, requires a small amount of fission on the inside as well. So they have a small fission bomb that goes off to kickstart the actual hydrogen bomb in and of itself. So to make it up, though, a hydrogen bomb this uses nuclear fusion in order to release large amounts of energy. So scientists, they are attempting, though, to harness this energy. They can't do it very well right now. Now, we do have abundant resources to start this, because they say, we only really need hydrogen to get going from this. So the hydrogen, deuterium, and tritium, we can get this by processing seawater. We can get this out of the ocean, and that will be our fuel from it. The only byproducts for this one would just be helium. So they said, hey, if we just get helium from this, that's a safe byproduct. We can use this over and over and over again, and it's good, and it's a good source of clean energy. It's inexpensive because we can get it from seawater, and there's not this radioactive material because we're using hydrogen to make helium. There's not a lot of dangers for it. It would be good, clean, safe energy. Unfortunately, though, it's really hard to do because it takes a lot of pressure and a lot of heat to get going for it. So as of right now, it takes more energy to get it going than it actually makes, so it's not super practical. Plus, whenever you have the fusion of deuterium and tritium, it produces stray neutrons, and so because of that, it'll eventually cause the radioactive material or the shells containing it to become radioactive. So your book points out it'll eventually bombard the reactor walls and make them radioactive. So again, that's a process or a problem of trying to take these atoms, these isotopes, heat them up to really high temperatures and pressure, and then force them to go together. They're not sure how to do it very, very, very well. Because your book points out you have to heat them to millions of degrees. So because of that, it's extremely hot. So finding a device that can withstand that and force the hydrogen together is very, very, very difficult. So scientists predict though that it might be possible to do this by the year 2050. So about 30 years from now, loosely give or take. So again, they're still working on it, but maybe in your lifetime they'll be able to use nuclear fusion to power electricity. So that way we don't have to use coal power plants or nuclear power plants. We can just use fusion and get energy that way. All right, that's pretty much it for it with the idea of fission versus fusion. Think about fission sounds like division because it's one atom splitting into two. Fusion is whenever you're taking two atoms and putting them together. So with a nuclear reactor, they're using fission. Fusion is like with the hydrogen bombs, and even though they're having experiments testing this, we can't keep it going yet. It can't be self-sustaining. All right, next section really quick. All right, electrons and chemical properties. All right, so most of the time, whenever you have a chemical reaction, that's typically not involving the protons or the neutrons. Now, occasionally we'll use the protons and neutrons, but most of your chemical reactions on a day-to-day level are because of the outer layers with the electrons. That's where most of your chemical reactions are coming from. So whenever you have a chemical reaction, typically the number of protons and neutrons isn't changing, it's the number of electrons and how they're shifting, either being gained or lost, or how they're being shared. Alright, so make a note though, the outermost layer of shell with an atom, we call it the valence shell or the outermost shell. So valence shell. Make a note of that. The electrons in that shell are called valence electrons. So the electrons of the valence shell, they're known as the valence electrons. So that's nice and that makes sense. So make a note for it. Now the octet rule states that most atoms tend to want to get 8 valence electrons in that outermost shell. Now remember, some atoms, like if you have uranium-92, that if it's that if this is a neutral atom, how many electrons does it have? If that has 92 protons, how many electrons does it have to have in order to balance it out? 92 as well. So you have to have 92 electrons with that with a negative charge to balance it out. Now, that might throw you off thinking, well, if they only want 8, this one has way more than 8. Remember, it's that outermost shell. So as you have the electrons, as they fill in with the quantum numbers, some of those inner layers, because of the different orbitals and because of their different orientation in space, they can hold more electrons than just 8 on the inside. But weirdly enough, atoms tend to only want 8 in that outermost layer. They don't want more and they don't want less. They want 8 in that outermost layer. There is a reason behind it, but your book just doesn't get into it a whole lot this year. So just make a note that, okay, they want 8 in that outermost layer. No more, no less. They can have more in those innermost layers, but they only want 8 in that outermost layer. So make a note for that. According to the octet rule, most atoms tend to react to obtain 8 electrons in their valence shell. The 2 major exceptions are hydrogen and helium. Because hydrogen and helium are so small, they only have 2 valence electrons. Make a note for them that hydrogen and helium, these are the smallest one. These are the 2 smallest atoms. So because of that, they tend to only be satisfied and happy with those 8 valence shells in their electrons. And that's pretty much it. So just make a note for that. So hydrogen and helium, they're so small that their valence shell can only hold 2 electrons, and that's it for them. All right, we'll go ahead and we'll stop there because of the classwork. It's probably just about time. So I'll go ahead and stop there for you. I'll catch up. Don't worry about it. Your homework for tonight. Read pages, where am I at? All right, 132 through 134, 132 through 134. Answer on page 134 and 135. The section review 6.4, questions 6 through 10. So on page 134 through 135, the section review 6.4, questions 6